negative.
Oh.
Okay. I'll close that. Not letting me do that.
Do that first after this. I don't think I can.
There we go.
Oh, there we go.
It's probably his.
No worries.
His,
Yeah.
All right, I think almost everyone is here. I was expecting. We'll just wait 1 or 2 more moments and then we'll kick things off. All right, everybody, I think we'll get started. For those of you who don't know me, I'm Samuel Singer. I'm the founder and executive director of Wyoming Stargazing, and welcome. Thanks so much for being here tonight for our virtual, virtual World Above the Tetons Speakers Series. This is our 4th year of doing this, so we're really excited to be continuing this tradition in 2021, and still working on our lineup of speakers for this year. But the theme is going to be upcoming telescopes and discoveries that are likely to change our understanding of the cosmos. And before I introduce our speaker, just want to remind everyone that we're going to do some door prizes at the end of the presentation tonight. So everyone who's here has a raffle ticket for our door prizes, which will be some very cool stickers that were made in celebration of a 2017 eclipse we had. And these 3 stickers here made by some local artists. And then we'll also raffle off one of our board members, Mike Adler's astrophotography prints, which are pretty amazing. He takes all these images at his observatory here in Jackson. And so we'll be raffling off, giving one of those away in the door prize. So stick around after the presentation for those. And the other thing that I just wanted to mention is just a big thank you and shout out to the board of directors of Wyoming Stargazing, who helps to make these presentations possible, especially to Liz Mosley, who does a lot of the behind the scenes work to do all the logistics for the speaker series. So thank you much, Liz. And with that, I'll introduce our speaker for this evening. Dr. Nick Galitsky is a postdoctoral scholar at the University of California, San Diego, where he works with another one of our board members, Professor Brian Keating, as well as with Professor Kam Arnold on the Simons Observatory, which is what he's going to be sharing with you tonight. Nick got his bachelor's in astrophysics at Caltech and his doctorate at the University of Pennsylvania, and has worked on telescopes down in the Antarctic and now in Chile. So Nick, thanks so much for being with us this evening. I'll hand it over to you, and we are all yours.
All right, perfect. Thank you for the introduction. Get things started here. And there we go. All right. Yeah, so I'll be talking a bit about the observatory I've been working on for the last 4 or 5 years now. I'm making rapid progress, which I'll show you a bit of. And this is specifically microwave telescopes of the Simons Observatory. And I'll talk a bit about the science and the design and so forth. But what I first want to mention is kind of an interesting thing about astrophysics is how we kind of divide the field up. And in a lot of ways, it's by our science targets. Say you want to look at the Big Bang or cosmology or galaxies, stars, that sort of thing. There's these kind of divisions about what I'd call the science case, the science motivation. But another side that you see kind of divisions in expertise or concentrations in expertise is by wavelength. And this is especially true on the experimental side because a lot of the technologies we use tend to be specific to certain wavelengths. And so I'm really kind of give you a rundown of how we design microwave telescopes specifically. So this would be millimeter wavelengths. Microwaves, if you like frequencies, there are hundreds of gigahertz is the wavelength or the frequency of light we look at. And specifically that there's some kind of interesting peculiarities about this type of telescope. And I'm actually on this first slide showing you kind of a preview of what we're working towards in this, this talk, which is the 2 telescope designs of the Simons Observatory. On the right, you have our 6-meter dish, which is large aperture, which you can see actually staircases here to show you the scale. And on the left, these are our small aperture array, which is, this is basically the size of a garage door here. And what I want you to think about initially when you look at these is if they remind you of a telescope, are they what you would think of? And I suspect for most people, no. Usually, you think of optical telescopes, these big shiny mirrors, that sort of thing. Or maybe even radio telescopes, if you're getting a bit adventurous, these giant white dishes are similar to your satellite dishes on the side of your house, something like that. Whereas microwave telescopes have this kind of number of odd features about them that I'm hoping to explain to you. The first part of that, of course, is understanding what's motivating all this. And to understand that, you have to know, well, why microwave? Why millimeter? And that's pretty easy. That's because the cosmic microwave background, CMB, the cosmic microwave background, emits light primarily in that part of the spectrum. In fact, it's the brightest thing in that part of the spectrum. So what is the CMB? That's kind of the first big question here, and that gets to the Big Bang. So in the very beginning of the universe, we have some sort of event that we refer to as the Big Bang that we don't necessarily know a whole lot of details about. But what we do know is that early universe was this really hot, dense plasma. And it was so dense that light couldn't travel very far before it just bounced off something else. So if light can't travel, it can't travel to us. And so what you have to do is you have to wait for our universe to expand. And as it expands, it cools. And as it cools, eventually it kind of cools off enough that light's able to travel out from the CMB, from that area, to us, to our telescopes here, through the rest of the universe. And that happened about 375,000 years after the Big Bang. So there's this period that's we refer to as the CMB. It's recombination, whatever else you want to call it. That is kind of like the glowing ember of the Big Bang. Big Bang happened, really hot, dense, then cools off and eventually releases light out that we're able to observe today. And why is that so exciting? Hopefully it's already exciting. You know, we get a look at the beginning of the universe. That's pretty cool. But there's a lot, just a huge amount of very fundamental science we can do with this. Just in that this was a very early stage of our universe. It's very telling about the physics, the initial condition of our universe. So that's really interesting. It also serves as a backlight to the rest of the universe. So we can use it to observe like galaxy cloud evolution through the rest of the universe. But the one thing I'm really motivated by and that what I'm really looking into is something called inflation, which perhaps some of you have heard about, perhaps not. But this is this class of theories that discusses the first fractions of a second universe's existence, in which it's been postulated that the universe expanded incredibly rapidly in a period of time. That would have left this imprint of signals, if we're going to dive into it, that we call them primordial B modes. It's a polarization pattern on the CMB. But effectively, really faint signal imprinted on the CMB, the light from the beginning of the universe, that we might be able to, and that might tell us about the first fractions of a second of our universe existence. So those are all just like, that's scratching the surface of what we can do with the CMB. It's incredibly exciting to go look at, a very motivating science case. So, all right, then we need to go build some telescopes to do that. So talk a bit about that. Here are some telescopes in Chile at our site, the Polar Bear telescopes. And this gets into our first thing about the CMB is, at first glance, it's not super interesting. And that's because it's incredibly uniform. Anywhere you look in the sky, you see the same thing if you had microwave eyes. And that is what we refer to as a temperature. This is when I said glowing ember, the CMB cooled off, released photons. And as that light traveled to us, the universe continued to expand. That effectively stretched the photons out as well. So what we see today is from that hot early universe, we now see an early universe that is effectively at a temperature of 2.7 Kelvin. It's about -450 Fahrenheit. So it's a very cold and with a peak emission in the microwave. And it's incredibly uniform. I should say that's really interesting of its own right. Before this kind of observation that we had this incredibly uniform microwave sky, the Big Bang theory was not dominant. This is one of the things that made the Big Bang theory the foremost theory. Okay, so that's a really interesting observation in its own right, but it would be great to delve into more detail. And we do that by looking at temperature fluctuations. So perhaps many of you have seen these kinds of images, kind of like a Rorschach test for physicists. You know, see what you see. But effectively what this is showing is deviations from this temperature. So this is kind of absolute, and this is fluctuations, deviations away from it, where the coldest, you know, the bluest spot there and the reddest spot here have a difference of a few hundred microkelvin. And that is to say the signal that you're looking at in this map is 1 part in 10,000. It's an incredibly faint signal. So this is setting up some of the challenges we have of looking at it. It's incredibly faint signal. Another great visualization I like to use of the CMB is this visualization from Dylan Berger, which shows that the entire CMB sky wrapped into a sphere. And this is just so cool to look at because we're at the center of the sphere just by how we observe the universe, right? So the Earth is at the exact center, and the entire observable universe, everything we can see with our telescopes, is inside the sphere. That's everything. The radius of the sphere is 14 billion light years. And that's just, artifact of the CMB. The CMB is as far back as we can look. So this is just kind of an idea of what it looks like on the sky, what we go after and look like, and the little temperature fluctuations that we've observed. So let's get into a little bit of history here, because this is also kind of fun, and also from the experimental side. It was discovered in 1965 in New Jersey, the Holmdel Horn. In the last 50 years, we've had 3 satellites, a whole slew of ground-based and balloon-borne observatories that I couldn't fit in one slide if I wanted to. But just a few of the highlights here. These are the 3 satellites down here, some of the balloon-borne ones. And then there's right now, there's a kind of 2 dominant groups, one working at the South Pole and one working in Chile. And what I want you to focus on here is looking again at all these different telescopes and thinking if they remind you of telescopes you've looked at before, kind of looking at their shapes, that sort of thing. I think the South Pole Telescope here kind of, almost looks like a radio telescope, but not quite. And what's also interesting, just from a historical perspective, looking at the Holmdel-Horn, some of the principles they used to set up their observatory have not changed in those 50 years. We still use some of the techniques they developed. So that's kind of an interesting part of the field. Okay, so now let's actually get into designing a CMB telescope. What does that look like? And the first part is, we're driven by the science. Ultimately, that's what you got to pay attention to. And I'm going to skip a whole section of our research, which is connecting science requirements to instrument requirements. That's a big part of what we do, is how does it drive what we look at? So skipping over that section, because that's a whole nother talk in its own right. But the first thing to note is science requires at least a 6-meter size telescope to look at small cells. So here I've got a nice picture of the Crab Nebula and the resolution of a 6-meter microwave telescope on that. So it gives us about 2 arc-minute resolution. But not only that, we not only care a lot about small scales, we care about large scales as well. And we care a lot about sensitivity at large scales. But it turns out that just via the requirements and what we look for, you can't do the same thing with both a large telescope and a small telescope. So we need 2 types of telescopes. And that includes a 1/2 meter size telescope, which is hilarious because a 1/2 meter in microwave has a resolution of about 20 arc minutes. At which point I can tell you that we do actually use the Crab Nebula as a point source for calibration. The next thing to know is, just basics of a CMB. It's 2.7 Kelvin. It's very cold. It's very faint signal, even if it is the dominant signal across the sky. But really, the hard part is, again, not the absolute signal, but we're looking for fluctuations, little deviations in that signal to 1 part in a million. And this gets into the kind of sensitivity we need. This is the challenge of the instrument that we need to achieve, is to be able to discern signal differences in 1 part of the sky to the other part of the sky to 1 part in 1 million, at least. Really, we want to do better than that. So there's some big challenges here. To add to that, we can't just do this at 1 wavelength. We found that in order to separate out some contamination and some other issues, you really need at least 6 wavelengths that we need to look at. So we actually look at 6 wavelengths from 10 millimeters to about 1 millimeter, which is an order of magnitude in spectrum, which actually adds a lot of complications to building telescopes that can cover that wide of a frequency range. And that is roughly, looking from a blue to the red part of the optical spectrum if you shifted it to microwave. So, okay, so these are all the big driving requirements that are based on what we want to get out of the CMB. Now let's go design our telescopes. How do we get to where we look at? The first thing is, let's start with the basics. Kind of everything on the table here. Are we using a refractive or reflective system? And this is just are you using lenses or mirrors? Your classic telescopes, a nice kind of Galilean style refractive, Dobbs, reflective system. So the first thing to think about, we have 2 aperture sizes we need, 1/2 meter and 6 meter. Can you build a 6 meter lens? You might be able to, but you sure don't want to. So, okay, we're not building a large lens. We're not going to use a refractive system for the large aperture. So that's going to be a reflective system, obviously. How about a 1/2 meter lens? Can I do that? Yeah, I can. The technology's there and it's not so bad. However, lenses have an issue, right? Different wavelengths are bent through the lens by different amounts. So I can only use a refractive system. I can only use lenses if I have multiple of them for different wavelength bins. But that's not impossible. I could do that and help me, if I want to get more detail in sky, maybe that's a good way to divide things up. Okay. So this is just to say refractive is on the table for my 1/2 meter aperture, as long as I have several of them and only use it for the 1/2 meter, and the reflective is for the 6 meter. The next big challenge gets into temperatures, which is going to be a kind of constant theme here. This is that the floor is lava. This gets into what is a black body, which I always kind of harp on about, but this is a very basic physics idea that we're all familiar with, even though most people don't know it by this terminology. But a black body is something that perfectly absorbs radiation and then perfectly emits it. A good example of that is a charcoal briquette. It's black, it absorbs radiation really well, it absorbs light. It also emits well. You just have to go to the infrared to see it. Or you can heat it up, and we're all familiar with that. Once you heat up a charcoal briquette or a piece of wood, something like that, it glows. That's blackbody radiation. That is, you've heated it up enough that it's just emitting a spectrum based on its temperature. And there's two things to know. The hotter something it is, the shorter wavelengths it emits at. And the other thing is the amplitude, the amount of light emitted also scales with the temperature. So another good example is an incandescent bulb. You just heat up a filament, it emits light as long as you heat it up enough. The probably best example of what we call a black body, which is a little counterintuitive, is the sun. The sun is about 5,000 Kelvin or 10,000 Fahrenheit. It emits with a peak in the visible spectrum, and it emits a lot of light. Cool? All right, so now let's find a good example a little lower down. Here I am with a cold beverage, and I'm emitting in the infrared. Humans emit really bright light in the infrared. We're 300 Kelvin. We're a little bit warmer than the room around us, so we're bright if you go to the right wavelengths. Okay, now this gets to our challenge, right? This is 300 Kelvin. We're going to the CMB. The CMB is 3 Kelvin, negative 450 Fahrenheit. It emits in the microwave. It also doesn't emit necessarily a lot of light compared to anything that's hotter. And so this gets into a challenge of, what if my telescope's hot? What if the ground is hot? And it is, it's room temperature. It emits quite a bit of light. So we have to be very careful about how we illuminate our telescopes, how we are able to observe the CMB. So to set this up in another way, I want you guys to all picture, everyone to picture going outside on a nice sunny day and close your eyes and try to find the sun. And you could pretty easily. You hold up your hand and you find the part of the sky that's really hotter than the rest of the sky. Pretty straightforward. The sun has really good signal to noise on the rest of the sky. All right, now do the same thing, but with the moon. We're gonna have a hard time. The moon's hot compared to the rest of the sky, but your hand's much hotter. So the only way you can get around that, cool down your hands up, put in liquid nitrogen, and sure, no problem, you can find the moon. All right, not recommended to try that at home, but in principle, it would work. So this is kind of how we go about observing the CMB, is you kind of think that the signal we're trying to look at is really faint signal. And the best way I can look at it is by eliminating background noises, eliminating things that are hot compared to the CMB. And by doing that, by cooling our telescopes down, like physically cooling our telescopes down, we get a much better signal noise on the sky. And this is also thinking about eliminating anything hot that's around my telescope or that's in the field of view of my telescope. So this starts to get to some of the oddities about microwave telescopes. Okay, so let's talk about a refractive system. I said now this is a half-meter telescope. Can I cool this whole telescope down? Can I get this whole thing cold enough that it's no longer really noisy for me? The answer is yes, I can. I can encase this in a special device and cool it down, have a cryogenic camera, and that works great. Next question. My reflective telescope is 6 meters wide. Can I cool that down? No. 6 meters is a lot of telescope to try and cool down. I am aided by one thing though. Now, when I said a black body is a perfect absorber and emitter of light, not everything is a perfect black body. In fact, a mirror is pretty much the opposite. It's very good at reflecting light, so it does not emit much. So as long as I'm using mirrors and I'm only looking at the mirrors, I should be okay. However, this gets into an interesting thing about most reflective systems, is I have this pesky secondary mirror that can't just float in space. It has to have mechanical attachments to it, and those are bright, and those are a problem. So I want a system that gets rid of the supports. And this is one of the things that if you've been paying attention to all the CMB telescopes, almost all of the reflective ones, we call off-axis. And this is just to say, I've taken my normal telescope and you cut it in half and you only use half of it. And so this means the path the light travels to my camera is unobstructed by anything physical. It makes the design somewhat more complicated, but it means I can support my secondary mirror down here and my primary mirror up here, and I don't need any struts or supports that get in the way. So off-axis mirrors are the only way to go, really, for millimeter reflective telescopes. Okay, Now we should talk about how do we take a picture in the microwave, because this factors a lot into what our telescope designs end up looking like. And this gets into another challenging thing. There are ways to do it coherent, if you're familiar with that, like radio telescopes. There are detector technologies and camera technologies that use similar things to capture that information. But by and large, the most sensitive measurements we've been able to make is if you're cooling down the whole telescope anyway, or at least the camera part of it, then you might as well cool your detectors down to get better sensitivity and use technologies that use cold detectors. So what we typically use is a bolometer or some variation thereof. And bolometer just means bolometer, heat meter. It just measures heat. And this is the very basic principle. Here's an early detector from NASA JPL on a dime. It's, small, but it's microwave scale. So these are large pixels compared to, say, an optical telescope anyway. And this little spiderweb pattern here is just to effectively absorb the photons. So photons come in here, get absorbed by a spiderweb or an antenna, something like that. And they transfer their energy to this little central device, which is basically just a really good thermometer. So we just use a really, really good thermometer. You collect photons, the power from the light itself heats up the thermometer. By how much it heats up, you can tell how much light you've absorbed. Simple enough, but your thermometer has to be really sensitive and it has to be colder than the light that's coming in. So that 3 Kelvin of the CMB, we got to be colder than that for our cameras to work. So now we're talking about really cold cameras, which then gets us into what is cryogenics. Perhaps you've heard this. I'm a specialist in cryogenics. I do a lot of this, and it's just generally referred to as the branch of physics dealing with the production and effects of very low temperatures. In short, it's getting things cold and keeping them there, which is challenging because most things do not want to stay this cold. It's loosely defined as temperatures below 93 Kelvin or about -292 Fahrenheit. So it's chilly. Can be used to freeze bodies, not recommended. We like using it for telescopes, but often that's the context it's heard of. Or Mr. Freeze, if you're a big Arnold Schwarzenegger fan. Gotta advertise that coming from California here. Okay, so this gets into where are we at now? So for a 1/2 meter aperture, we've decided we want a refractive system. That's pretty good. It actually has some benefits. It can fit, we can make the whole thing cold, which is nice. So that solves a problem for the camera aspect because the whole thing's already cold. Now the camera's cold. All right. This does mean for a 6 meter dish, however, we need the camera itself to be cold. So, okay, the whole telescope, we can't cool that down. It's too big. But the camera itself, we can cool down, so we can use that detector technology to make the most sensitive measurements. So we start giving you an idea of what this actually looks like. So this is starting with the basic, schematic. And I should say these are ray traces. These are tracing where the photons go to 2 of our actual optics designs for telescopes. So here you see the light coming in from the one brings it, starts to a focus, and then a field lens brings it to a focus on the detector plane. So 2 lens system in a cryogenic system. So these are all these layers around it, keeping it and the detectors cold, no big deal. Here's about, I think this is a 5 or 6 meter dish, primary mirror coming in here, this off axis system, bringing it to a secondary and bringing it to a focus at the camera, where this camera is cooled down, even though the whole telescope is not. Okay, so now we're starting to get into what it actually looks like. All right, obviously that's not that simple. Let's get into a little bit of the technology that goes into making these cameras and these telescope systems and achieving all these things that I've laid out that we have to do to get that really rich CMB in the most efficient way we possibly can. Okay, so I told you we have a camera and it needs to be cold. How do we do that? The first thing you need to do is you need to go buy a really expensive refrigerator. Of course, if you're going to buy a really expensive refrigerator, cool your camera down, you want to make the best use possible. So you add a lot of plating layers. So this is kind of the basics. Wrap it in a bunch of different layers. As long as you're there, you might as well remove all the air because air conducts heat and you don't want that. So these are vacuum systems. So now it's under vacuum, a vacuum chamber in here with an expensive refrigerator cooling down all these layers to cool your camera down. Unfortunately, add some supports that transmit some heat, but you can use special materials to reduce that. We need to record the data, obviously. So you have a bunch of wires coming out of there. We can't use copper, that conducts too much heat. So we use special materials in those wires to connect it, the camera detector system to our computers to record the data. And then probably the most painful part of this whole process is how do we get the light in? And that's a big challenge because you've just made all this effort to keep this thing cold. Then you cut a giant hole in the side of it, and you still got to stay, keep things at very cold temperatures. So we have special materials we use for windows that can hold the vacuum pressure. And then we have special filters that basically reflect infrared light, but allow microwave light to transmit. So there's a whole bunch of techniques we use to actually make this whole system work. And so now I kind of want to get into, well, what does this actually look like? So these are kind of two telescopes. I should say this is the Atacama Cosmology Telescope, precursor to Simons Observatory. This is the BICEP Telescope, also precursor to Simons Observatory. And this is actually our designs. This is the Simons Observatory designs. Once you've factored all those things in and try to maximize your science case, these are cutaways of the two telescopes. Well, remember, this is ½ meter, so I'm about as tall as this telescope, where this one is 6 meter, and that's a door there. So this is a big telescope. Okay, so first on the small aperture, which is what I work on. I've done a huge amount of work on this design. We're building the first one here at UCSD. And the first thing to notice is it's a refractive system. 1, 2, we have 3 lenses, actually. We had an extra lens in there to improve our quality. And the detector system. This is our expensive refrigerator, which I'll talk about later. And this big red thing is the vacuum chamber. And you can see the multiple layers in here to kind of protect us from, to keep everything cold. What's exciting about it is actually how cold do we keep our optics? Our optics, all lenses are at 1 Kelvin. So this is, again, down to negative 450 something Fahrenheit is our entire optical system, just to really control that background light. And this is, I should say, this is just really the camera element of it, although it is the telescope itself, camera and telescope kind of in one, because all the lenses are self-contained, and it looks directly at the sky. And then the 6 meter telescope is actually really interesting optical design, and it's a few things change. One is, if you're building a 6 meter class dish, they are very expensive to make. Obviously, this is, the size of a large house. It's a 3 or 4 story building that's a telescope. It's expensive. So you really want to maximize your utility from it, which is another way to say, we've made our detectors as good as we can get. The only way we can get better sensitivity now is by increasing the number of detectors. The way you do that on a large telescope is by increasing your effective focal plane, your field of view here. So what we do, how we accomplish that is with this very specific optical design called a cross dragone. And what it is here's our primary mirror is a 6 meter mirror. Our secondary mirror is also a 6 meter mirror. And effectively what that does is it makes a focal plane, a focal area that is 2 meters across. And so this camera, the camera for this telescope, is a 2 meter wide cryogenic system. That's also about 2 to 3 meters long. It's huge. It's one of the largest ever made. It's a really amazing device. What's also kind of interesting, though, is this kind of gets into the nitty gritty of the optics. But if I really wanted to take advantage of the prime focus of this telescope, I'd have a 2 meter wide window. I cannot make a 2 meter wide window. That we talked about that. That was a bad idea. We don't want to do that. So instead, what we do is we actually have to refocus the light once it gets here onto our detector planes. And we use lenses to do that. So this is where, for some people, this will be a new term. A catadioptric is just to say a system with both mirrors and lenses. It's neither refractive or reflective. It's both. And this is using a lot of the technologies for the small aperture telescope in the camera for the large aperture. And just to give you a cross section of this camera, again, I can walk inside this camera. It's huge. The primary focus of the telescope comes at this plane with the hexagonal windows. And behind those windows, we install a series of these modules we call optics tubes that contain 3 lenses and the detectors. And so then we have this nice modular system. You can now have different, I talked about those different wavelength bins. So we have, not each one of these, but we have a division of which one of these is which wavelength that we use. So that allows us some fidelity in how to choose that as well. And so those are kind of the basics of the telescopes and the cameras we use. Getting a little bit into how do we get that cold, because that is a kind of cool way to do it, pun intended. The basic way, and the way we use for many years, is using liquid nitrogen. That gets us down to 77 Kelvin, and liquid helium gets us down to 4 Kelvin. Hilariously, we call these wet systems because they use liquids, even though it's liquid helium. I've used wet systems. They're an absolute pain because liquid helium is this, it's a magician of sorts, a Houdini. It likes getting out of its containers. So it tends to be very difficult to work with. So we've moved away from that into what we call dry systems, which uses kind of tricks of physics to remove heat. One of these is this pulse tube system, which effectively uses pulses of helium gas and a pressure gradient to remove heat. And that can actually get you down to 4 Kelvin, which is one of our kind of base temperatures we build off of. So now you can just buy these as a commercial system. Not only that, recently, in the last, say, 20 years or so, another commercial system has come online that's used extensively in physics right now, which is called a dilution refrigerator. And a dilution refrigerator uses actually a quantum mechanical effect to kind of a dilution of helium-3, an isotope of helium, and another isotope of helium, helium-4, to remove heat. And it cuts down to the base temperature that you can get here is 5 millikelvin. So this is, again, getting to the Kelvin scale. Absolute zero Kelvin is as cold as anything can possibly get. These systems can get to within 5 parts of 1,000 to that temperature. So they're really good at getting down there. We don't go quite that cold. Our detectors that we design operate at 0.1 Kelvin, a tenth of a degree above absolute zero, but I'd still say pretty darn cold. So that's where our detectors sit. And we use both these technologies to cool down our cameras. What does that look like? Well, here we are in the lab. This is us actually installing our dilution refrigerator, just dropping it into the system. There's also a pulse tube right there. And then here you can see it on the inside, where each of these gold-plated stages is a different temperature. This is a 4 Kelvin stage, this is a 1 Kelvin stage, and this is our base stage at 0.1 Kelvin. So very fun to be able to see it to come together. And then I didn't mention too much about the electronics. We'll see if anyone on here is kind of interested about this. But this is our first test pixel we had in the smaller aperture telescope. And these are pictures from my lab at UCSD, where you can see the wires coming out. We use a lot of coaxial or SMA connectors if you're interested. So a lot of RF engineering goes into how to actually extract, I kind of set up the type of detector we use. It basically measures this very small changes in the temperature here from photons hitting it. And then you have to extract that signal out into multiple layers. So what you see here are these different rings or different temperatures as we get the signal out of the telescope and boost it along the way. We have amplification at different stages. Then it goes up to here, and there's a whole nother set that brings it out the other temperature stages and out of the cryostat, out of the vacuum chamber. And here you can see also the cold heads where we cool things down. The 4 Kelvin one is encased in this little box here. All right, so that's kind of the basics of what it looks like. But let's talk a little bit more about how do we insulate it, because that's kind of a basic idea. And the basic thing is, if you want to insulate something well, you want it to be a reflective, so it reflects heat instead of absorbing it. So you don't want the inside to do that. Just the kind of basic schematic, we add a bunch of layers of insulation, and that's reflective insulation that effectively reflects the heat back, lowers the emissivity of the interior layers. What does that look like in principle? It kind of almost looks like NASA or a satellite that you'd see, right? What we call is MLI, multi-layered insulation, which is just many layers of this super thin aluminized mylar that reflects radiation out. And then, so that's all these silver layers. This orange thing here is really cool filters. So this is where the light comes in. This is the type of filter we use. This is about 60 centimeters across. So, it's big. It's a big filter. And what they do is they reject infrared radiation and allow millimeter radiation to pass using kind of this mesh of copper on a substrate. So not to get into too much of the details, but they're really cool technology. There's one place in the world that makes it. Cardiff, Wales is where we get those from. And they've developed the techniques to build this type of filters that are used in microwave telescopes around the world. So very cool. Getting into the telescopes themselves, so just kind of pointing out the different stages now. So dilution refrigerator here, vacuum shell here. We have a 40K shell as well, 4K shells, the insulation layers. This whole section at 1 Kelvin, windows and filters up here, and that couples this focal plane where all the detectors are where we use these hexagonal modules. And there's 7 of those, and it's about a 40 centimeter wide camera to get about 20,000 pixels, or I should say 20,000 detectors. It's a better way to put it. So yeah, we use tens of thousands of detectors, and that's huge for us. That's a whole nother range. But again, of course, detector size scales with wavelengths. So comparing that to optical is not fair. Of course, with the small aperture telescopes, which I work with extensively, they're no good if you can't point them on the sky where you want to. So I did kind of want to call out the kind of the rest of how they look, why, or the reason why they look the way they do. And so first thing you do is you mount them, and you can actually see the telescope / camera mounted here. It's mounted on the azimuth stage. That's just to say pointing side to side. An elevation stage, which points vertically. And we actually have a third axis of rotation called a bore sight, which actually rotates our camera along the optical path. And we do that because the polarization signal specifically that we're going after, that 1 part in a million signal, that's very faint. By allowing that rotation, it actually allows us to control for what we call systematics, which are artifacts of the instrument that might be imprinted on the signal. And so it's one way to control for that. And that kind of all this other stuff that's hanging out around our telescope. Why not just have the window out there? And that's because the floor is lava. Everything around here is hot. And so we really want to control the illumination that our window. So we actually have 3 layers of protection to make sure that the window or the light coming out of our telescope is only looking at things we know it's looking at. So that's this 4-baffle in front, which is basically just a giant cone of shame that's attached right onto the front of the window. The elevation co-moving shield, which is a whole nother shield to prevent stray light from the ground. And then just to be extra paranoid, we have this ground shield around the whole telescope, which does 2 things. It blocks light from warm things, like we're on the shoulder of a mountain, so the mountain peak itself, we're worried about light from that hitting our windows. So this is high enough to block that, as well as actually acting as a windshield, because it gets kind of windy up there, and that helps us with some other stability. So that's why it looks the way we do. This is just a little refractive telescope that's embedded in all this shielding to control the amount of other light that's not the CMB light that we're looking at from getting into our system, so we can make these incredibly precise measurements. I also always like showing this because I actually work on the design and make these kind of designs. It's always very satisfying when you can convert the design into reality. So this is, again, another picture of the telescope we have in our here at UCSD, where you can see some of the wires coming out here. And this is all cryogenic systems. These are all part of the cooling systems that pop out the top here. And the window is hanging out up on the top here. We've made a lot of progress recently. Obviously, we have a telescope here. I should have thrown in a picture from today. Today, we installed the optics. I looked at one of our silicon lenses today. They're really kind of crazy to look at. And if somebody asks that question, I can probably bring up a picture if I've uploaded it from my phone real quickly here. But that's kind of where we at. We now have a telescope in our lab because now it has the optics. And what's even more exciting is this is recent progress from Germany, where they're building this whole pointed platform. So you can see the shape of where the camera goes in here. This is the backside axis for the electronics. And this is sped up by 10 times. This is our typical pointing scan. We point to a side and scan back and forth and scan this little patch of sky that is kind of the best optimized for the science goals we're going for. So that's coming along. And this is kind of getting into future notes here. We're obviously hard at work, as hard at work as we can do during the pandemic. We've had some limited lab access, of course, and other challenges in the last year, certainly supply chain and all sorts of fun stuff and rescheduling, what have you. But we still managed to make quite a bit of progress on the instrument. And we're trying to ship it out, the first one to Chile in the end of this year. And this is just a look at our site, which is high and dry is our motivation. This is at 17,000 feet altitude. I get to say we're the 3rd highest observatory in the world. The first highest is CCAT Prime, which is down the road from us. They're on the next peak over at 18,000 feet. We're at 17,000. And there's a odd little Bolivian telescope that's at like 17.5. So they just barely beat us out. Anyway. 3rd highest observatory site in the world. We actually have 3 CMB telescopes here already. So these are kind of the previous generation, and we're building the next generation Simons Observatory right here. And I can assure you this section no longer looks like this. It's been excavated, and I was actually just on a call today where they're showing us pouring the foundations for the small aperture telescopes, which I'll tell you, the nuances of our work is, it turns out it's hard to pour concrete at 17,000 feet. you learn some things, but it's all part of the fun. And that's just kind of a quick overview, yeah, of what the Simons Observatory looks like, what we're after, some of the larger science goals, and what's next is getting all those experiments down to Chile. Hopefully, starting the end of this year is when we'll be shipping things out. Oh, fingers crossed. So at this point, I'll open up to questions about any and all of that, the science, the instruments, and the Simons Observatory. Thank you.
Thank you, Nick. That was pretty cool stuff. Those telescopes are a lot different than the ones Galileo was building 400 years ago.
Some slight changes to the system, although still using refractive optics, which I always find hilarious.
Yeah, that's pretty cool. There's an image of one of Galileo's original telescopes that was brought up to the International Space Station by astronaut
cool.
Scott Altman, and he took it up there on the last repair mission of the Hubble Space Telescope. So he's holding Galileo's telescope, and you can see the Hubble Space Telescope in the background out the window.
Very cool. We'll look that one up.
Yeah. Well, anyways, I'm sure folks have got questions, so feel free to unmute yourself and ask away.
Yes. See you raise your hand from Sally. There you
go. We can't hear you, Sally. You're not muted, but there's no sound.
Oh, maybe the phone's muted.
Okay, is that better?
Oh, that's much better.
Okay, so I was just wondering about the way the Keck Observatory does that laser beam thing that helps sort of get rid of a lot of the wiggles in the pictures. And I wondered, are you guys doing that kind of thing in future telescopes? Thanks.
That's a great question. Adaptive optics. So actually you can kind of see that here. So this is referring to the lasers they shine up to make a point source, an artificial star that they can then use to correct their mirror shape by actuators on the mirror that fluctuates the mirror shape to correct for atmospheric variations. That's actually a great question. The reason we're high and dry is because the primary thing that absorbs microwave light is water vapor. So we're very sensitive to water vapor in the atmosphere. That's why we go to great lengths to get to these altitudes. And the basic answer is an optical telescope. You really have to worry about that to perform a really precise image. But in microwave, you can be a lot lazier about it because we just need that 2 arc second or 20 arc minute resolution, if I quoted those right. But our resolution requirements are far lower. So really what you do is you just build your mirrors to get you that resolution, and the distortion from the atmosphere doesn't matter as much to us. Because it's less that's for looking at point sources or very small things. We don't mind a hidden resolution. It's okay if our images are blurry as long as they're the right amount of blurry. Is kind of the best way to describe that. It is interesting.
And the humidity level makes a difference then in the air.
Yeah, so we can avoid a lot of that just by the fact that we're up high and dry. Not that it doesn't come into it, and I'm actually kind of pointing out with my laser here that you can see the 6 meter mirror, which you can kind of sneak peek through the aperture here. You can see almost a bunch of grid pattern. That's because our mirrors are composed of a bunch of separate panels. So our meter dish, actually both the primary and secondary and the 6 meter dishes have something like 60 aluminum panels each on a carbon fiber backing structure, and they are actuated. We can control the mirror surface, but the way basically we just do that occasionally to check if it's out of shape. So we do want a consistent shape to the mirror surface that we do analyze, that we look for, and we are able to adjust for. We just don't do what you were calling out, which is active. We don't do it as we're observing. We do it occasionally to make sure our beam quality is up to our specifications. So we do incorporate some of that technology, but not nearly as aggressively as optically telescopes do. Great question.
Thank you.
Oh, can't hear you, Sam.
Oh, thanks, Sally. Anybody else have any questions? Yeah, Dr. Little.
So I had a question, and as this has to do with whether things are changing in cosmology, and that is that I read but didn't absorb too much of I think it was in Scientific American, that cosmology was changing because the as best I can understand it is that the factors that go into the making the Big Bang theory work, and the expansion of the universe and the rate of expansion of the universe don't quite add up, and that what is taken to be dark matter, whatever that is, whatever is taken to be dark energy, whatever that is, and the visible universe don't quite add up with the constants that I think it's the Hubble constants that they've been using for some time to calculate. So where is that now? Is that
No, that's a good question.
I'm not even sure how to ask the question, but
I get where you're driving at, and we'll see if I hit the right notes here. I can say it is a very exciting time to be a cosmologist, specifically because there are so many unknowns, and you rightly call out that the only reason we call it dark matter and dark energy is because we have no clue what it is, where it's coming from. And this does factor into Big Bang cosmology and the kind of fundamental aspects that we know. So kind of the basics that we derive from Big Bang cosmology, or to put it another way, the constants, the physical constants that parameterize how the physics of our universe at a very fundamental level work, have been incredibly well measured. And those are remarkably consistent between multiple experiments and that sort of thing. So I would say we know a lot, and we've discovered a lot, especially in the last, say, 50 years. But obviously, there's these huge questions. You raised up one of them, which is the Hubble constant, which is one way to measure the expansion rate of the universe. And there's two kind of dominant measurements of it right now with supernovas and with the cosmic microwave background. The CMB has been providing some of the best measurements of that particular number for many years now, and now you're seeing a disagreement in the early universe. And so the first question we as cosmologists ask is, did we mess up our experiment? Because usually that's why. And so, that's the less exciting possibility, is that the experiments were missing something in the design or the aspect or how they go about measuring it. Increasingly, however, with that particular one, the Hubble constant tension, it's looking like it's a real thing. So that means that was something we were not expecting. And what we'd say is it points to new physics, which is just to say our theory of the universe that we had before does not explain it particularly well. And now we need a new theory, which for theorists is great news. For observationalists, arguably great news too. It means, well, okay, so one set of experiments found tension. How else can we look for it and find if that's a real thing, or how do we piece it out from different types of theories? So I think that the answer is, there's still a huge amount we don't know. Dark matter, dark energy, the Hubble tension, and also the Big Bang itself is a very interesting question. I think you kind of alluded to some of the tensions there, where one of the signals we're going after, that inflation signal I mentioned early on, this rapid acceleration in the beginning of the universe, we haven't seen that signal yet. There were theories that would say, you would need, I said we're looking at like 1 part in a million, and now it's become a fraction of 1 part in a million. And it's like, well, is it that the signal is fainter and we're going to find it eventually, or is it not there because the theory that we thought was the best explanation is not right? And so now there's other classes of theories that you talk about. There's some big proponents of this is, naming conventions are kind of fun in physics. Hate them or love them, but you got the Big Bang competing right now against the Big Bounce, which is another kind of class of theories about how the universe not necessarily formed, but is more just evolution. It compacts, it bounces back, and that's what the Big Bang was the bounce back from a really dense state to where we are now, and that's a cycle. A lot of people kind of like that because then to have a cyclic universe is more satisfying from a science perspective as far as, you know, if it was the Big Bang, what caused the Big Bang, and getting into whether we'll be able to observe that. I think on the technology side, on the observation side, obviously the digital revolution has just done insane things for telescopes and what we're able to look at. You know, the technology we use for our detectors, the data processing capabilities have just become milestones since I began my career. You know, it's just insane to watch the progress of the field. You know, this is kind of funny. My advisor, that level advisor, they could get this is kind of the joke in our field, that you could get a thesis from building one detector. And now I'm building systems that have tens of thousands. You know, that's effectively a generation of scientists. You've come to several orders of magnitudes in the number of detectors we're putting into telescopes. So that kind of gets at to, you know, this really faint signal we're looking at. It's funny to look at some of the original theory papers that predicted it. They said, oh, there might be this really faint signal that would tell you that this event happened just after the Big Bang. But it's not particularly interesting because we'll never be able to observe it. And we've already passed the limits they predicted. So it's really, and I don't know if that's a satisfying answer to you.
What is your theory?
What is my dominant theory? I really would like inflation to be there because then I can find it and that would be fun. Perhaps a little bit of a selfish explanation, but it is nice to be able to find that's just to say an observational result is always more exciting than a null result, even though a null result is really interesting and telling of its own right. We are already talking about the kind of next generation of these telescopes. How do we improve even more on what we have? And we're starting to design that because it's just such an incredibly compelling thing to go after. If that doesn't find it, I think at that point, it's almost like to put it another way, there are other noise sources, you know, just in the universe kind of thing that become incredibly hard to get below. And at that point, it will have ruled out this whole swath of theories, and we're going to have to think, you know, not start from scratch, obviously, but rethink our impression of how the early universe formed, which will be really interesting, really exciting time to be a part of it, even if it's not quite as exciting to be able to observe the thing I was trying to observe.
And we don't have any idea yet what dark energy or what dark matter are. Is that still true?
No, and I think of the two, dark matter is particularly confounding because if it is something with mass, you'd think we'd be able to detect it. And that's a whole, you know, I don't work on those, but I pay close attention to them because they use usually cryogenic systems as well. So one of those xenon 1 ton, it's cooling down this giant vat of liquid xenon on the off chance that one of these dark matter particles will hit one of the xenon atoms and release a little flash of light. These are just kind of the ways you can detect dark matter potentially. But there's these fun diagrams that basically show it uses energy, but you know, mass and energy are similar, right? It's like the possible theory space of where dark matter could exist, and they're starting to rule out pretty big patches of it with no detections. And so, you know, I would say as the field, we're like, wait, it's gotta be there. Where is it? And it's, you know, it's kind of this weird cosmic accounting. It's like, you check in our books to make sure we didn't miss it somewhere. But in that sense, our universe is interesting because it is contained and we kind of know how it began. It's like, if you produce this, it must have been produced somewhere. So
it's supposed to be the majority of the universe, right?
Yeah. Oh, well, yeah. Dark matter is a huge amount of the mass energy content of the universe. It dominates over normal matter, and so it just doesn't interact. So you know, that makes it obviously very challenging to observe. And you know, again, whole classes of theories about what it could be, and because you know, in a theory, you can't just have, oh, it's a particle of this mass. It has to be, where was it made? How did it get there? How did we get so much of it? So again, it's like making sure your books are balanced. So it's a huge question about on both sides of that, what it is, and what it is that's where most of the focus is observation, trying to observe at kind of what energy scale, what mass scale this exists, because that'll tell a lot about where it could have come from. But both sides of that are big open questions, and there's a lot of experiments going after that result, which will be interesting. Dark energy is a whole nother thing of really getting at the fundamentals of our universe. And it started, I would say the theories are there, and we're getting into the place where we can start having observations that might be able to rule out some of the theories. In fact, you can do some of that with CMB science, but it's more challenging. It's kind of thinking a little more forward about how we can possibly measure some of the effects that dark energy might have that would point to its source, and kind of almost more fundamentally how our universe formed and evolves, which ties right back into the Big Bang and that whole Big Bounce theory as well. So yeah, so it's fun, it's exciting, but challenging.
Good enough. Thank you.
Yeah, great question. Keeps me employed for a while anyway.
Well, that actually brings me to the question I wanted to ask you.
Ultimately, that's probably the right thing, right?
Yeah, I'm okay with it.
So I kind of wanted to piggyback on the question that Dr. Lowell just asked, and you partially already answered this, but I'm curious about, what the ramifications of the two potential outcomes of the data collected by the Simons Observatory. So one, you find the polarization and the cosmic microwave background radiation. That's the smoking gun that everyone's been waiting for inflationary theory. So you prove inflationary theory, maybe, that's what I'm asking. Maybe. Does that actually prove inflationary theory? And then does it also, you already, okay. So the other part of that question is, and then how does that fit in with providing evidence towards the existence of the multiverse?
Getting into the multiverse, right? So this is a lot of the theorists, or the I should say field that is the big fan of, say, big bounces or other explanations, is because that gets really nuanced, and I'm not gonna probably. If you want me to, I can go ahead having a try at explaining that. But this is kind of a consequence of a lot of inflationary theories. Is by natural consequence, you get a multiverse, which is just to say it basically creates these bubbles of universe, and there's an infinite amount of them. And so then a lot of people don't like that from a scientific perspective, because it says that anything is possible, and that this is just a coincidence, this universe exists, which is not necessarily a very satisfying answer. I think my perspective on that is I'm not sure the universe really cares if we're satisfied or not. But so it could be the explanation. It is inflation, and you end up with multiverses, or it could be a class of inflationary theories where you don't end up with multiverses. Although that's challenging to achieve. And then to kind of, that is in your question about whether if we observe this signal, does that mean inflation existed? No. Theorists are I think that was a great quote from I say theorists as like there's whole other people. They're just people that work in our department that focus more on blackboards than telescopes. But that theorist said it was something like, what observations can we do that will best constrain your theories? And their response was, it doesn't matter. Whatever you observe, I will have theories that will fit it. And that is to say that even if we observe it, does that mean that it's only inflationary theories work? No, there are other ways to produce that type of signal, certainly. I think it just becomes more challenging, and it certainly would fit with, this is the kind of thing with the Big Bang inflationary universe that we're working with. It really does a good job of explaining pretty much all of the observables we have. And so of the class of theories we have, it really matches up a lot with what we've seen so far. So that would be nice to have that kind of fit too. If it's not there, then it becomes more challenging to have that as an explanation. It really forces us to bring forward a lot of these alternate explanations about how we produce our observables without this rapid expansion in the early universe. And a lot of people would be rather satisfied by that, frankly, because again, there's a class of people that just do not find a multiverse, producing theory to be particularly satisfying or particularly the best explanation. So I'm more on the observation side, which is all those theories sound very interesting, and I'm interested in what signals I can go after to reduce the number of theories that we can have. And so I think from that point, what Simons Observatory will accomplish, it will accomplish that. We're driving down that limit much harder, and kind of where we chose our limit, which again drove all of our instrument design, all the design of the instrument, was kind of at this natural crossover point where this large class of theories that are kind of the most simple theory of inflation would be ruled out. And so that's kind of, if we won't necessarily rule it all out. In fact, there's something called CMB S4, stage 4, which is the next generation of CMB telescopes that I'm also part of. That would go even farther down, so there is still space to go experimentally to look at this, but we'd really rule out a large section of it and really, I think, push the field of cosmology to rethink this. So that's certainly what we're trying to do. And it'll be interesting. Yeah, stay tuned. In 5 years, we should have pretty much everything on Sky and results out in about 10. So moving as quickly as we can on that anyway. Yeah, great question, though.
Nobel Prize in 2030.
Yeah, there we go.
I just had one more quick question, and you should be able to answer it pretty easily. But who is your favorite? What was your favorite science fiction work, and who was your favorite science fiction author?
That is a great question. That is relatively easy to answer because, yeah, I got into science fiction early on. Arguably, that was one of my bigger inspirations to get into science nonfiction. Probably that's probably the right order it went in. I think my favorite author as a kid was Arthur C. Clarke. Love Arthur C. Clarke. He's, I think, an amazing author, and one I really appreciated with because he worked within the constraints of our universe. He went with, he can't travel faster than light. All right, we'll work with that. We'll make science fiction. He's the guy trying to figure out, well, how do you get a toilet in space working? That kind of level of detail. And I think that really made some really fantastic works, as well as some really philosophical works about how we think about it. I think my favorite books from him were the Rama series. I really enjoyed that one, even though I think it's somewhat lesser known. But if you're looking for a good sci-fi series, I love it. Yeah, the Rama series is amazing.
Okay, that takes care of me. And I think Sally's got a question, and I'm going to sign off. So I appreciate it. Thanks, Nick.
Of course. Thank you for the questions. Have a good night.
Okay.
Being here.
Yeah, actually, I was going to ask that question too. Hold on.
Anybody else have any questions for Nick?
Sam, you're on mute.
Stuart, did you have one?
Yeah. So just to follow up with, I mean, you're right. I mean, of course you're right about the theory part, that we have a lot of theories that, like with string theory, that still we can't, it's not testable yet, but mathematically it's nice. And I don't know if you read Stephen Hawking's last book, where he was trying to come up with the Big Bang and how we could get something from nothing, and variations of vacuum energy where, anything is possible given enough time is a certainty. So, but it seems like, that's a lot of theorizing to come up with the Big Bang, but I haven't really heard the Big Bounce. That's different than, there were old theories called the Big Crunch, about the universe expanding, then contracting down. What about the Big Bounce? Can you just say more about that?
Yeah. I think I'm trying to think of, I guess in our subfield, the guy known for as Steinhardt. I think I don't want to claim that with.
You mean the guy from Princeton? I thought.
Yeah, the guy from Princeton is one of the people who voices things like that, and I think I read a paper by him in the last few years where he kind of detailed it. It's kind of a combination of the Big Bounce and Crunch, or Big Bang and Big Crunch, right? The basic principle is kind of playing around with energy. It gets confusing because it's like shape of the universe and four-dimensional shapes and so forth. And vacuum energy, and ways you can manipulate that such that the universe, basically squeezes back down, and you have this huge energy density and that sort of thing, and our modern physics breaks again, and then it bounces back out. And so what we're in a bounce cycle where we see it, and at some point in the future, it will crunch down again, and it will repeat that. So it's a kind of repeating cyclic event. I think the more modern ways of the Big Bounce are a little more, shall I say, nuanced than that in terms of how they accomplish that with the kind of what we know about dark energy, which is not a lot, but at least that there's vacuum energy and that we can play around with that. as well as incorporating some of the more modern observations of, say, the CMB and that sort of thing. But you know, and I think that's the point. Any good theory replicates observation. So it still has a rapid period of expansion in the early universe. It's just, instead of something from nothing, it's something from a previous version of our universe that compacted down. And the way, you know, there are challenges in the mathematics about how you actually accomplish that given these certain constraints of observation and the theories we have. And I think, oh geez, you know, now you're testing me. It's like, I have this paper, I'm pretty sure it's Steinhardt, and I'm trying to remember what exactly he was saying in that, because it's a good paper. But it was I'm not going to be able to get it. I want to say he got around, I can't remember if he got around it or not. I know he addressed, or he mentioned it anyway. Which is, you know, one of the other big questions of physics, which we don't really touch on, is a big part of the Big Bang. And one of the reasons it's so confusing is when you get a universe that's so, when you get any point in the universe that becomes so dense, you kind of break modern physics, because quantum mechanics and general relativity stop agreeing with each other. We don't have a unified theory. So if you've heard of unified theories or that sort of thing, that's something that combines these two, you know, massive pillars of modern physics that make sense of things like black holes and the Big Bang, where you have them crossing over on similar scales. And that's also unresolved. You know, we don't understand what happens there. And I think that factors into some of these theories about the Big Bang, about the big bounce, is how do you resolve some of those differences? I'm not sure that answered your question about like kind of what the big bounce is. This kind of gets into modern shape. And I think, you know, the part I'm kind of grasping at here is there was an explanation of how the increased vacuum energy or the expansion of the modern universe plays into that. Like that observation was incorporated into these series of big bounces, but I forget exactly how, and I don't have a good way of describing it. So that's a tough question, but a good one.
Well, just to follow up on it, you reminded me of this cosmologist. I think his last name was Davies, from Arizona or something, and he wrote some books about trying to figure all this stuff out, the beginnings of the universe, and whether God exists or not. And he ended up by saying that any theory that you have about the beginnings of the universe is going to sound crazy, you know, just because we don't know.
Yeah.
Yeah, but you know a lot more than me, and you're really have just studied all this stuff. We're probably all going to die without every question being answered. But what do your guts tell you right now? You know, I know you're trying to get observational data, not theorize, but I'm pushing you to get to the other pole and theorize a little bit more. I mean, what do your guts tell you about how you put it together?
That's a great question. How do I, kind of like, how do I feel about the theory space, or what kind of my favorites or that sort of thing? You know, I think how do I feel about that? Because I've gone back and forth on this too. In Big Bounce, it's like we're this self-contained and closed thing, and that's kind of interesting and nice. But then the kind of whole inflation spawning, you know, multitude of multiverses, getting, you know, that this question, and I think to me that's always kind of a fun one, is what's outside our universe? Is there an outside our universe? And this kind of the bigger questions about, you know, how is it all contained, and where does it come from, and where does it evolve? I don't necessarily have a favorite of that. I do enjoy about it, and I always say this is where it crosses over from physics to philosophy, and it's always some very enjoyable discussions to have there, and enjoyable to see how different theories approach that kind of boundary in terms of a science. You know, it gets into like, what is science? What is being a scientist mean? You know, can you live with a theory that predicts that anything is possible? Is that legitimate, and that sort of thing? And, you know, I find, I don't think I have a real favorite, which is maybe a cop-out, but I just enjoy reading them. I just enjoy reading about them and learning about them and thinking about them. And of course, you know, having an eye for what might that tell about our universe, and thinking about what if there are ways we could observe it, right? What if there's a way, what if there is a multiverse and we find a way to observe that multiverse? How cool would that be? You know, this is getting way out there because we can't even figure out what dark energy is, but but it would be exciting. And I think you're right. You know, as much progress as we're making, I'm going to die before we figure out a lot of this. But it is fun to be part of that journey and see the evolution of thinking in modern science. So, yeah, that's a great question. Thank you. Do my best to answer it.
Thanks, Stuart. Thanks, Nick. Let's do some raffle prizes and the drawing, and then if we still have a couple minutes after that, and there are a couple more questions for Nick, he can answer them if he's so inclined. But speaking of progress in telescopes, I wanted to show you that image that I was mentioning earlier about Galileo's telescope with the Hubble Space Telescope in the background. So there it is. So that's one of Galileo's telescopes up on and inside Space Shuttle Atlantis, and through the window there is the Hubble Space Telescope. So 400 years of progress from the very first telescope that we know of that was used to look up at the night sky and actually record observations. There were earlier telescopes that weren't used for the night sky, and maybe even people who looked at the night sky but didn't actually write down what they were looking at and tell people about it. So that's what Galileo did with one of these instruments. And 400 years later, we put this huge space telescope orbiting the Earth, and both of these telescopes changed the way we see the universe. So kind of fitting to start with this image with our series this year about telescopes and discoveries that change the way we think about the universe. And stay tuned. The Simons Observatory may join that class of telescopes shortly. Yeah, cross your fingers. All right. So the raffle and the door prizes. So first we'll raffle off 3 of these stickers. Or excuse me. First we'll give 3 of these stickers away for door prizes. One of the prints away for a door prize. So 4 door prizes. And then we'll do the raffle drawing for another print. So for this first sticker here, Chasing Totality, the winner of that sticker is Ian Edwards, the Wyoming Stargazing Board of Directors president. Just grab my pen here, write that down. All right. And for the second sticker, the Jackson Hole eclipse, the winner will be Nicole. I think she left the meeting earlier, but I've got her contact information so we can get that to her. And the Cowboy Eclipse sticker, lucky winner of that one is Stuart Sugarman. Nice, Stuart. Okay. So now we'll do a door prize for one of these amazing astrophotography prints. And the way this works is that if you're here in town, if you're local, we've got a bunch of these already printed out on some foam core, and you can actually I went to the wrong one. If you're local, you can actually pick one of these ones out that we all have already printed, and you can just come pick it up from our office. If you're not local, we can have one printed for you and we can ship it right to you. So any one of these pretty amazing astrophotography images, and you can see all these up on our website if you go to the shop link. So for one of these prints, for the door prize, lucky winner is Vicki Becker. Congrats, Vicki. Vicki, are you still online with us here? Well, hopefully we can find her. All right, so now we're going to do the the raffle drawing for one of those prints. So if you you bought raffle tickets either for this event or for previous events, you've got your name in this other jar of raffle tickets here. So I'm going to pull one out for another astrophotography print. And the winner is J.R. Dalby. JR bought 20 raffle tickets a few months ago, and this is not the first print that he's won. So there you have it. If you buy a lot of raffle tickets, your chances of winning one or two or three increase dramatically. All right, well, we're just coming up on 8:30. We got about 9 minutes left. Any last questions for Nick before we wrap things up?
Samuel, it's Ian. Can you hear me?
We can, yeah. Hi, Ian.
Hi. So I have a question. Yeah, the image of the cosmic background radiation. Have people done any research to ensure that it's truly random? It's assumed that it's random because the cosmic fluctuations, but have anyone poked around to see if there's structure in that?
That's a great question, and I think the answer is yes. They've looked into this. So this gets into a really intriguing aspect of CMB physics. So I'll just share the screen here again. Okay. So getting back to the CMB here. Rotating. Oh. So this image, I think this spot is called the cold spot, and there's some other places like that where you're saying like, well, why is that spot so much colder than the rest? What are some of these over or under densities that we see, real? Is that or is that just a statistical anomaly? And this is getting into the fact that the CMB, we only have one CMB we can observe. And so these, especially the really large scale ones, it's a question of the statistics of it. If I took, X amount of random spots in our universe, what are the chances you would see this particular distribution? And is it, low enough that you can say, no, this is interesting in physics, or is it just a random fluctuation? And it's a really challenging aspect of the field because the only way you can do it is, change the fact of where we are in the universe is go somewhere else in the universe. If we were able to travel 2 billion light years further over, man, that would be fantastic. We could get some really great data and results and compare and learn a whole lot about, the kind of fundamental statistics of our universe. Unfortunately, we can't do that yet. So we're stuck with it. And that is a question. That is actually really fantastic question. That's a big challenge for us. Is just, we get one set of statistics, that's it, and you've got to do what you can with it.
Right, so your telescope is going to have, I think, 1,000 times more resolution and temperature, right? Did I get that right, from a millidegree to a microdegree?
Yeah, roughly speaking, yeah.
And so the image you should create is going to have, I'll use the term, more depth to it.
Yeah,
yeah. And that might show something we can't see right now. Yeah,
I'd say there's kind of two ways. So this image I'm showing here is from Planck. It's, the way you can tell it's a satellite is it's all sky. Obviously we can't do that from the ground. So from the ground, the large aperture telescope, the 6 meters, looking at something like 40% of the sky. So it's a survey instrument where we scan just a giant swath. And then the small aperture telescope, it's really about that depth. So we focus on about 2 patches that cover about 10% of the sky. So it's still a survey instrument, just more focused. Where do we go? The thing about Planck, which was the last satellite observation, is they had polarization capabilities, but they were not optimized for it. And so one of the ways we are able to get that sensitivity is not so much in the temperature signal. So I would call this is the temperature signal, which is to say this is an absolute intensity. It doesn't focus on the polarized signal. we can do that order of 1,000 better effectively on the polarization signal, and that has encases the information about these primordial fluctuations and some other, kind of fundamental physics, as well as reconfirming kind of through a different observation the underlying physics of the temperature signal as well. So that's a big section that we're able to do. Plus, and that's especially those small aperture telescopes just drive deep, so they really, our temperature measurements honestly won't be that great. It's our polarization measurements that we're really optimizing everything for, because that's where these big science cases are. The other place where you can get a lot of science cases you couldn't get from the from Planck is it was a satellite, so it did not have a 6-meter mirror. So in one way, we'll get more depth on this field through their sensitivity. In the other way, we'll actually get better resolution. We'll be able to resolve some of these blobs, even smaller blobs, on the sky, and we call that the damping scale. But the small angular scales actually contain quite a bit of information about the early universe as well. Some kind of odd things like neutrino physics, and that's that type of information that we can pull out of that. So those are kind of the summary. Polarization and angular scale are 2 ways we can improve over the satellite observations. Good question.
Thanks, Ian. Anybody else? The last questions for Nick. All right. Well, you either totally convinced us or totally baffled us, Nick.
Hopefully the former. It's either way, it's a fun time to be an astronomer of any type.
Totally, and I'm just glad to get to learn about this stuff from folks like you. So, Nick, thank you so much for being here and sharing your knowledge with us, and thanks to everybody for being here and joining us for these events. Wouldn't happen without you, so really appreciate you being here. Stay tuned for who we're going to have in February. We haven't figured it out yet, but in the next week or so, we'll announce that. And we hope to see you again in February for the next World Above the Tetons speaker series. But until then, have a great evening and take care. See you next time.
Thank you.
Bye.